unit, surprisingly. But that's actually a good thing when you think about it. If you have something that's really easy, being a really important part of a current unit, that's probably not a bad thing, right? Okay, so, end behavior model, the whole blurb is kind of spelled out for you, but what it's basically trying to tell us is that a function will behave like its end behavior model for extreme values of x. All right, so whatever the end behavior model is, which is almost always a simpler function, it will have a behavior. It will behave. All right, for values of x that are large in the positive direction or in the negative direction, as in going out to infinity or negative infinity. All right, the behavior of that end behavior model will dictate the behavior of the original function. All right, so I'll show you real quick. Looking at part A here, the end behavior model, it's very simple. You get it by taking the term with the highest power on the top of the fraction and dividing it by the term with the highest power on the bottom of the fraction. All right, so the EBM here, we would get that by taking x and dividing it by x squared, simplifying it. The end behavior model would be 1 over x. All right, so what I'm telling you here is if we were to take that y equals 1 over x and just look at the characteristics of that graph. All right, it's got a horizontal asymptote, it's got a vertical asymptote. We don't really care about what's happening around 0. We care about what's happening for large values of x, all right, in the positive and negative direction. So I can go out to positive infinity. It looks like it's approaching 0. All right, if I get some points along the graph, it becomes a little bit more clear. All right, so values that are pretty close to 0. I could also go the other way. You kind of convince yourself, all right, this one's also approaching 0 just from the low side. All right, so it's increasing to 0 rather than decreasing to 0. All right, so the question would be, well, how does that connect to the original function? So let me turn that off and take a look at the original function. I'll put it in as f of x. So fraction x plus 1, x squared plus 3. All right, two vastly different looking functions around 0. All right, they don't look anything alike. In fact, I'll turn the other one on. That around the y-axis, they look nothing alike. All right, it's like, how can you use one to estimate the other? But as you go out to infinity, you see that they've practically merged. Now, they haven't quite merged, all right, but they're pretty dang close. Now, as I get really far out, so I'm going to zoom out, and I'm going to scroll over and then zoom back in. It takes a lot more zooming in order to show that they're different from one another. I had to zoom in a lot there. All right, so this is the red, 0.000667, and let's see if I could even get on the black. Nah, still the, yeah, there we go. Yeah, practically the same. All right, off by the slightest margin. All right, so for extreme values of x, they're actually going to the same location. They're both approaching 0, but they're actually approaching each other too. All right, so what this actually gives us is the ability to figure out the limit as x approaches infinity for a complicated rational expression by looking at a much simpler rational expression. All right, so if you have a choice in the matter, obviously you'd rather work with a simpler thing. If you know they're going to behave the same way, then why not work with the easier one? All right. So looking at B, the end behavior model, we would get that by turning on our highlighter tool. The term with the highest power, top and bottom, including the sign. Don't forget the sign. So the EBM, I'm going to use a colon there. Y is equal to negative x squared over negative x. Simplifies down to just y equals x. All right. So this weird looking rational function is actually going to behave exactly the same way as just a line y equals x. I mean, there's hardly any line in existence that's easier to work with than y equals x. Maybe the x-axis and the y-axis. All right. But y equals x, that's not difficult to work with. So I can look at my original function, g of x, fraction 4 minus x squared over 2 minus x. It actually turns out that it is the line, or it is a line parallel to y equals x. It's actually the line y equals x plus 2 with a hole in it at x equals 2. And if you just kind of scroll over that location, you'll see that there's a hole at x equals 2. But it will behave exactly the same way as the line y equals x. All right. As you go out to infinity, they're both going the same. They're both going the same place. As x goes to infinity, they're both going to a y value. If you could ever get to a y value of positive infinity, that's where they would be going. All right. So this end behavior model could be used to find asymptotes, horizontal asymptotes. It could also be used to find what we call infinite limits. All right. I put the recall there. Just a little refresher on how you find horizontal and vertical asymptotes. Definitely take a look at those if it's not fresh in your mind. However, I can tell you that these rules, now that we know end behavior model, the rules for horizontal asymptote are now obsolete. We don't need them anymore. All right, because the end behavior model will tell us if there is a horizontal asymptote. All right, so let's take a look at an example or several. We'll see. How about, I'll just start with number 1. Keep it simple. All right, so the limit as x approaches infinity of 5x plus 4 over x. All right, we want to do this what we call, in a way that we call analytically, which means that we don't want to resort to creating a graph. All right, we want to use the algebra of calculus, if you will. All right, so what that means is for cases that involve infinity, we want to find the end behavior model. All right, so the end behavior model here is just going to, again, we take our expression and take the term that's got the highest power on the top and divide it by the term with the highest power on the bottom. All right, so we have, I'll write it as f of x, 5x plus 4 over x. We're going to take that and only pull the terms 5x and x, pull those out. That'll give us our end behavior model by dividing them. So y would be equal to 5x over x, which gives us y equals 5. All right. So what we're saying here with this approach, because they will behave the same way, meaning f of x, that f of x is equal to 5x plus 4 over x, and y equals 5. They're going to behave exactly the same way for large values of x in the positive or negative direction. Instead of saying, let's find the limit as x approaches infinity of 5x plus 4 over x, let's find the limit as x approaches infinity of 5. Right? The limit of a constant is equal to a constant, so the result is actually equal to 5. So let me just show you graphically real quick. So we have f of x is equal to, same deal, 5x plus 4 over x. Now you might recognize that there's a horizontal asymptote here. You might even recognize that it's at y equals 5. All right, that's what I was saying, that these horizontal asymptote rules on the previous page, if you remember from pre-calc, well, one, if you remember the horizontal rules from pre-calc, I mean, congratulations. I mean, that's an achievement in and of itself. Because I can tell you that when I was a calculus student and the teacher said, oh, you remember the horizontal asymptote rules from pre-calc? I was like, we didn't learn those. There's absolutely no way we learned those. And I'm convinced to this day that we didn't learn them. Because you spent like 5 minutes on it. You know, pre-calc and gap, probably even less time. So I mean, if you remember these rules, I mean, you have a pretty good memory. All right. If the numerator's degree is more than or less than or equal to the denominator's degree, do this, do that, do the other thing. We don't need that anymore because we know limits now, or at least we have a sense of limits. If you understand the concept of end behavior, which is really, it's a term, it's a nice term, it actually defines itself. How does the graph behave at its end? All right, well, there's two ends. There's the one going out to the left, as in negative infinity. There's one going out to the right, as in positive infinity. So that's definition of asymptote. All right, horizontal asymptote, if it levels off anywhere. All right, so what we just found, y equals 5, by finding the end behavior model, we found the horizontal asymptote. All right, that would be the horizontal line that the graph is approaching. Wonderful. So if I'm looking for the limit as x approaches infinity, I would just scroll, and take a look to see what y value the curve is approaching as I go further and further to the right. Graphically, it appears that it's leveling off at 5. All right, so you can get it graphically, but we want to get to a point where we can do it analytically. All right, number 2 is very similar to number 1, so let's take a look at same deal with number 3. Let's take a look at number 4. All right, so same idea, the EBM, end behavior model. We're going to grab the term with the highest power, top and bottom. So I'll rewrite f of x, so I could use my highlighter. All right. So the term with the highest power is a zero. Jeez. Just making stuff up now. Term with the highest power is an x on the top. The term with the highest power is an x squared on the bottom. Divide those two, and you get y equals 1 over x. Very similar to the example we did on the previous page, except now we're going to the next step. We're saying, all right, since we know that the original function is going to behave the same way as the end behavior model, why not, instead of working with this, which isn't really a nice looking function, let's work with something that's much simpler. All right. Now, this isn't as simple as the limit of a constant is equal to a constant. We have to make a substitution here. But now I could actually substitute in an infinity for x. Right? So I would say 1 divided by infinity. Now, the funny thing about infinity is it presents itself as an actual number, a finite value. But it's infinite, infinity. Right? It's a moving target. All right, infinity's on the move. You take one step towards infinity, it takes one step away from you. All right? So we want to be thinking about this conceptually, because really what this is saying is we're going to divide 1 by a number that's getting bigger and bigger and bigger and bigger and bigger. So we would ask ourselves, all right, well, what's that going to give us as a result? And again, a limit is not talking about what a value is. It's what a value is becoming, or would become if it could get there. It
would be approaching 0.
It would be approaching 0, exactly. All right, so if you don't recognize that, there's a way to handle it. You could do it with Desmos. You could do it on the TI. I think it's a little nicer on Desmos because you could use a slider. All right, so if you just type in 1 over a, 1 divided by some constant value a, add a slider for it. All right, so tap on a, the slider. What it'll do is it'll compute 1 over a for you for a various set of a values. All right. So if I slide my slider to the right, you could see that it's decreasing in value. All right. It's just a question of how far will it decrease. All right. So you can change the parameters on your a slider. So tap on the low bound, make that 0, because we only care about positive numbers anyway, or non-negative, and make your max a value, make it something large, like, I don't know, 100. And then start sliding your slider and see where it's going. This would simulate a value moving out towards infinity. The a value is moving out towards infinity. You would be thinking about, where's my fraction going? It's decreasing. It's getting smaller and smaller and smaller. The only thing you'd have to reason out is, okay, well, what is it getting closer and closer to? And the further you go out, the more obvious it becomes that it's getting closer and closer to 0. All right. So that's a nice little nifty advantage to Desmos. Number 5, same idea, except different outcome coming up. All right. So M behavior model. So f of x squared minus 2 over x plus 1. All right, bringing it in. We know by now that we're taking the term with the highest power on the top, dividing it by the term with the highest power on the bottom. So that's going to give us y is equal to x squared over x, which simplifies down to just y equals x. So the EBM shouldn't be the hard part. It's the interpreting of the limit. That's the tricky part. All right. So this piece here, you look at it and say, that's a pretty complicated looking expression. I'd rather work with something much simpler. Well, this x looks a whole lot simpler. Let's work with that instead. Through direct substitution, this one just presents itself, or presents you with the final answer immediately. Because if I replace the x, direct substitution, replace it with a negative infinity, substitution, I'm going to get a negative infinity. So I'm able to do that without creating a graph. All right. You could always check your work with a graph, but if a question asks you to do it analytically, you're going to want to make sure you take the time to do that. All right. So that was a little bit of a review / extension, because you've definitely, in pre-calc, you've definitely found limits as x approached infinity. I don't know that you ever did it this way. All right, so I wanted to make sure I took the time to show you the more advanced way / the more calculus-oriented way of finding a limit. All right, so that's kind of what we're building towards. And then tomorrow we'll tackle analytic limits where we're approaching a constant. So what I want you to do is take the time to continue working through the packet. You should be good to go through page 10 at a minimum. You could also try to problems past page 10. Our goal is to get through page 14 by the end of class on Wednesday. All right, so in your small groups, you're working together, you're asking me questions, you're asking each other questions, et cetera, et cetera. So enjoy the process, folks. I'll stop the recording.